the Robotics Institute seminar. It is my great pleasure to welcome Meg Schwager to the seminar as our speaker today. Meg is currently an associate professor of aeronautics and astronautics at Stanford University. And there he leads the multi-robot systems lab. Meg, I will not read your full CV. It is amazing, but I want to tell instead a story of how I met you for the first time.
Great.
You may not know this story because I met you the first time in the audience of a Toyota Research Institute seminar that involved projects from MIT and Stanford. And so we all were there. And I was sitting next to one of your graduate students. And the typical thing, if you sit next to a graduate student, is that at some point they don't listen if their PI speaks because they have heard it 5, 10 times. But it was not the same thing with you. With you, it was different. Your graduate students did not only listen. When I was really impressed about the talk, they were eager to confirm and said they think that they have as a supervisor one of the best speakers they have ever met in their lifetime. And
wow.
I know that graduate students at a university such as Stanford are spoiled by hearing good speakers all the time, but I still
you know how much I pay them to say that, right?
Sorry?
You know how much I pay them to say that, right?
Well, yeah, so I mean, you must be doing at least at this a good job. Because they seemed really convincing. So they must have been they are doing a good job at that. And I was also very impressed at the talk, and I did not receive my payment. Yeah, so something went wrong there. And we're very excited to hear you speak today. You worked on so many cool topics. On autonomous driving, on cooperative robotic manipulation, on other multi-robot systems such as cooperative surveillance with SUVs. We share one piece of common past in the sense that we had the same supervisor. For me as a postdoc, for you, I think Daniela was your PhD supervisor at MIT. Right. And you did also all your degrees there. And you stayed in Boston initially for your assistant professorship with a brief postdoctoral stop at UPenn. And right. Then you went on to Stanford. Meg has won many amazing awards, NSF Career Award, I think the Young Faculty Award of DARPA, and also wrote a huge amount of super interesting papers that also won many awards, which I will not count. I'm very excited personally about the topic you will be talking today. I think a lot of these developments in neural reconstruction will really heavily affect robotics, and you're one of the pioneers in the field of neural reconstructions applications for robotics. So I really very much look forward to your talk on reimagining robot autonomy with neural environment representations. Take it away, Meg.
That's great. Thank you so much, Igor. That's such a gracious introduction. And I'll do what I can to live up at least, half of the sort of image that you painted of me. We also have another crossing point in our history, which is that we had the same bicycle, but I'll leave that for another time. So I'll talk today, as you mentioned, Igor, about rethinking robot autonomy, and I mean that writ large: robot manipulation, robot navigation, and robot simulation, and how we can leverage new environment representations, 3D environment representations, which are basically representing 3D geometry as neural networks. And I think there's just a lot of exciting potential, but also a lot of challenging research problems in this space. So let's get my slides to advance. Okay, so let's talk a little bit about, at a high level, what do I mean by a neural environment representation or a neural geometry representation? So very simple concept. Basically, you have some 3D geometry and also potentially some 3D lighting properties, color, and so on. For example, for Stonehenge, and you store all that information in a neural network. That's the basic idea. There's a lot more complexity in there, which I'll talk about in a second. The concept can be applied to whole environments, but also to just objects. And you can imagine having a neural network that represents the geometry and color of a cup, and of a pencil and of a computer or whatever, and then you can think of composing these objects to build semantically sort of multi-layered 3D scenes. So I'll be talking about both of these ideas a little bit. And in particular, I'm going to focus on three thrusts in my lab that have used neural environment representations for sort of different sort of canonical tasks in robotics. So one of these canonical tasks is to navigate a robot through an environment when the map of the environment is stored as a neural network. The second thrust is to plan dexterous grasping and manipulation trajectories for robot arms or robot manipulators when the object that they're manipulating is stored as a neural network. And then the last is building a physics simulation concept where when you have objects that are represented as neural networks, how can you simulate the contact interactions and the motion of those objects when they undergo, when they experience forces and torques and undergo motion in a simulated world. So to give a little bit of context, I want to talk about existing geometry representations in robotics. There are kinds of pros and cons, and then introduce why these neural environment representations are different and potentially what they offer to us as roboticists. So firstly, one of the, I'd say, gold standard methods for representing 3D geometry is the triangular mesh. This is a standard representation, right? It's the representation that's most common in computer graphics and also in computer vision. And it's kind of the workhorse that is used to represent graphics in computer games or in, you know, CGI computer generated movies or animation and so on. However, it's a little bit less common in robotics because meshes are hard to build online from robot sensing data. It's hard to build a mesh directly from robot images from an onboard RGB or RGBD camera or from a LiDAR sensor. And it's also hard to correct meshes, right? So if you, oftentimes you may start building a map of a scene and find that you made a mistake because your sensor measurements were, you know, you were hitting a sequence of unlikely sensor measurements. And so you have to correct that mistake, and meshes are hard to correct in that sense. So instead in robotics, we tend to focus on point clouds, which are sort of the native data type that comes from LiDAR sensors. And then you have to stitch point clouds together and register them against some global frame. Or voxel grids, where you grid up 3D space into a bunch of little cubes, and then you decide if each cube is occupied or free, given your sensor data. And I would argue that there are limitations with both the point cloud and the voxel grid representations. One limitation of the point cloud representation is that it doesn't actually give you information about the interior and the exterior of objects. It just gives you points on the surface of objects. So it's a little ambiguous, especially if your point cloud is sparse. It's a little ambiguous as to where you can go and where you cannot go. And so computing or reasoning about collisions and computing collision-free trajectories can be difficult in point clouds. For voxel grids, I think the main challenge is that they're inherently conservative because you have to grid up space, and space is really a continuous thing. And also they can be very memory inefficient, right? Space is not very happy if you divide it up into little pieces. And of course you need, if you double the resolution of your pieces, you end up with 8 times as many voxel elements. And so the scaling does not work very well when you want to grow to large 3D geometries. So what's the idea of a neural representation? It's basically store all of this information that goes into 3D geometry in the weights of a neural network. And then you can continuously query this neural network to find out in continuous space whether or not some point is occupied. Now, there's a lot more that goes into this. So let me talk a little bit about the subtleties. So there are potentially a lot of different ways of encoding 3D geometry into a neural network, but really what I'll be focusing on in this talk is the concept of a NeRF, a Neural Radiance Field. Many of you have heard of this already. The concept is about 2 years old, 2.5 years old. So the first paper that introduced the NeRF was this one, Mildenhall et al., that I'm citing here at ECCV in 2020. So the idea behind this paper is as follows. You have a neural network. In the case of a NeRF, it's usually a fairly small neural network, like maybe a 5-layer, multi-layer perceptron with 256 neurons per layer. So, you know, in the context of computer vision, that's a fairly small network. And this neural network tries to represent the following map. So the inputs to this map are a 3D point in space, which is a query point. And basically, you want to find out if that point is occupied and what color that point contains if it's occupied. And then a viewing direction, which is the direction at which the camera is looking at that point. And then the outputs are the density, which is roughly sort of a differential probability of occupancy. You can roughly think of it like the likelihood that that point is occupied. And then a radiance, which is just a three-dimensional vector of color, RGB values. So the idea is that if it is occupied, here's the color of the mass that occupies that point. And the reason why this map is view dependent, meaning it changes its values depending on what direction the camera is looking at, is because of the radiance. Actually, the density is not view dependent. It only depends on the XYZ position of the point. But you can imagine that as the camera looks at a point from different perspectives, light is going to reflect off that point in different ways. And so you want to be able to capture the fact that it may have a different color or a different brightness from different camera perspectives. And so this neural network is paired with, I think actually the most important part of the NeRF is pairing it with what's called a differentiable ray tracing algorithm, or a differentiable rendering algorithm. And that differentiable rendering algorithm looks like this. So suppose that somehow you have the geometry and color represented in 3D space in this neural network. Then how can you render an image? How can you synthesize an image from this geometry? So the idea is that you consider a camera, which is located as I'm showing here. You consider all the pixels in the image that you're trying to render, trace a ray through a pixel into the 3D volume, and sample along the 3D volume, and your sample points are drawn with probability corresponding to the density. So higher density points are sampled with more likelihood. And then at every one of those sample points, you record the density and the radiance. And then you simply compute a weighted average. It's a little more subtle than this, but this is good enough for our purposes. So then you take each of the radiances weighted by each of the densities, and you compute a weighted average of the color, the weighted average of the radiance, and then you ascribe that color to that pixel. And you do that for all the pixels in the pixel array in the image. And the result is just incredibly impressive. So again, these are not my results. These are the original Mildenhall et al. Results. But the images that you see at the top, this is a sequence of images that looks like a video. These are entirely synthetic. These were just imagined images rendered from this NeRF neural network. And so what's amazing, of course, is how lifelike the images look, but also if you look at the depth map, which is what I'm showing below, it appears that this neural network is capturing meaningful 3D geometry information. So it looks, the parts of the image that are clearly closer are clearly represented as closer, and those things that are clearly farther are represented as farther away. And so when I first saw these results as a roboticist, I thought, well, not only is the NeRF good at producing images or good at producing pretty pictures, this is also a 3D geometry representation that we can use for robot navigation and for robots interacting with the world. So there's one piece which I haven't talked about here, which is how do you train this NeRF? And the idea is that you train the NeRF by taking a collection of images, and then you figure out where the cameras were who took the images using some standard structure from motion techniques. So those are called posed images. And then you train the neural network so that when you render an image from the neural network, the image looks as much as possible, as close as possible to the actual image that you took. And the difference between the rendered image and the actual image is called the photometric loss. And that's it. So you just do atom optimizer, stochastic gradient descent optimizer on that photometric loss on a collection of images. So the take-home message is that you can go out with your camera, take a bunch of images, throw them into a NeRF training pipeline, and produce a really high fidelity 3D model with color of that scene. And so that's obviously really powerful for robotics. So, so I'm interested, as I said, in using these NeRF representations for various robotics purposes. And I'm not the only one who's had this idea. So there's been a number of existing works. I'm just going to touch on a few works in this space. So I'd say one of the early works was called iNeRF, which was basically the following problem. Suppose you have a pre-trained NeRF and you take a new image can you deduce what the camera viewpoint was that took that new image? That's iNeRF. And you basically take the photometric error, the difference between the rendered image from an initial viewpoint and the true image, and you do gradient descent until you figure out how to minimize that photometric loss, and that tells you what the viewpoint is. You do gradient descent to optimize the camera pose. So this is very nice work. It came out right after the initial NeRF paper was released. It's from Alberto Rodriguez's lab at MIT. Then another really incredible early work in NeRFs applied to robotics came from Andy Davison's lab at Imperial College London, where he basically built a SLAM pipeline on top of the NeRF, using the NeRF as a map representation. So in real time, this algorithm, which is called IMAP, can figure out the camera poses and build the NeRF as the camera moves around. And then finally, there's been quite a few works now on using NeRFs towards robot manipulation. And so the work that I'm highlighting here is again from Alberto Rodriguez's lab at MIT. And basically it uses NeRFs as kind of a midway point to generate data for training a dense descriptor. And then the dense descriptor can be used for planning robot grasps. Okay, so the work that I'll talk about now is a bit different from all of these existing works. So I'm going to start by talking about our trajectory optimization algorithm for navigating a robot through a 3D scene when that scene is represented with a NeRF. So this is work primarily by the two first authors, Tim Chen and Michał Adamkiewicz, who are both in my lab. Michał's a PhD student, Michał's a master's student, Tim is a PhD student. And we have the following paper, but I can refer you to that paper for more technical details. So again, the main idea is that you're given a pre-trained NeRF of the 3D environment. Now, this is just a starting point, right? You can imagine that you could couple our trajectory optimizer with, for example, IMAP to obtain this 3D map online and then use our trajectory optimizer to plan through it. But, just for the sake of cleanliness, let's separate these two problems. Suppose we have a pre-trained NeRF. Then we want to optimize a trajectory for a robot to move through that NeRF while avoiding collisions and while respecting the dynamical constraints of the vehicle. So that's the trajectory optimization piece, but then there's the trajectory execution piece. So when you actually execute that trajectory, you need to know the pose of the robot at every point along the execution so that you can correct when the robot drifts away from the trajectory that you're trying to follow. And so I'll also be talking about a state estimation technique that's entirely based on the NeRF. Okay, so firstly, for trajectory optimization, really there are two important pieces here. Firstly, the trajectory has to respect the dynamics of the vehicle. The vehicle I'll be focusing on here is a drone, but you can also do this for autonomous cars or for ground robots, differential drive robots, whatever, or even robot arms, robot manipulators. But the part that makes this really difficult with the NeRF map is that you have to avoid collisions, right? So you have to make sure that the trajectory that you plan has a low likelihood of having a collision between the 3D geometry and the robot body. So what we do is we propose a collision metric using the NeRF representation. So we take the robot body, we sample points in the 3D volume of the robot body. So we kind of represent the robot as a point cloud. And then at each one of those points, and given a particular pose of the robot, we query the NeRF to ask what is the density at that point. And then we compute an approximate collision probability, which is basically the probability that any one of the points in this point cloud is in collision with the underlying NeRF. So that's that probability of the union over all events of the event that any one of these points is in collision. And then we upper bound this probability. So we find a sort of conservative collision metric by using the union sum bound or the Boole's inequality. They're both, the same concept is called those two names. To basically, instead of taking the probability of the union of these events, we take the sum of the probability of each of these events separately. And then each of these events, which is the event that any one point is in collision, we quantify by taking the density of the NeRF at that point, which is again like a differential collision probability. And then we multiply it by the arc length that point would experience between two successive time points in our trajectory. And this is important because you imagine points that are out at the perimeter of the robot. If the robot is spinning, they'll have a long arc length and they'll have lots of opportunities to collide. Whereas robots towards the interior, if the robot is spinning, they're not going to translate very much. And so they're going to have a lower probability of collision. So we multiply these two things, and this gives us our collision probability metric. And then we integrate that into a trajectory optimization problem. So our cost function is don't use too much control effort and minimize this collision probability metric, subject to the standard stuff. So subject to you respect the dynamical constraints of the robot. So the quad rotors can only move like quad rotors. And you have to start at the start point and you have to end at a desired endpoint. So these are the underlying constraints. And you can see that when you solve this optimization problem, here's kind of like a toy schematic of that solution over multiple iterations of the solve. So the initial trajectory, you see the NeRF density is represented. So high NeRF density is in black and low NeRF density is in white. And here, this is the kind of point cloud that represents the robot body. Initially, you're in a high likelihood of collision, and then you optimize the trajectory to get yourself out of collision while remaining in a dynamically feasible configuration. So the few little kind of side points, we explicitly use the property of differential flatness of the dynamics of the quadrotor. If that's not familiar to you, I would point you to the quadrotor planning and control literature where differential flatness is used quite often. So we use this to kind of numerically accelerate this optimization. And then another point that I want to draw your attention to is that we're using actually machine learning optimization tools. We're using the Atom Optimizer and AutoDiff tools in PyTorch to optimize this trajectory optimization problem, which is also a little unusual, right? Usually in robot trajectory optimization, you use like a Gauss-Newton's method or some other second order sort of higher powered optimization technique. We can't really do that here because the objective function nested within the objective function is a query of the NeRF. And so we need to be able to differentiate into the NeRF to be able to find out how moving the robot body points affects this collision probability. And so we need to be able to do AutoDiff. And so we've chosen to use the standard machine learning optimization pipeline. It turns out it works very well actually for trajectory optimization. Okay, so putting all the pieces together, there's a pre-processing step, which I haven't really discussed in detail, which is that we coarsely grid the space and we use an A-star search to find an initial path between start and goal. And that search can be arbitrarily bad. Like that initial trajectory does not have to be dynamically feasible. It can have egregious collisions with the environment. It doesn't matter. It's just to seed the continuous optimization. That's what you see here. So that purple curve is the initial trajectory. And then the relaxation is the solve of the continuous optimization. So you might ask, okay, you have this kind of collision proxy, which you're putting into your cost. How do we know that you actually avoid collisions with the environment? So that's what we studied in this in this set of numerical experiments. We basically trained a NeRF of a playground, children's playground structure based on a ground truth mesh, using images that we generated from Blender from the ground truth mesh. So now we have the ground truth mesh, we have the NeRF. We use just the NeRF to plan the trajectory, and then we go back and see if that trajectory collided with the ground truth mesh. And the take-home message is that basically if you tune the weighting parameter that weights your collision probability, if you tune that properly, then you find that it is a very good proxy for the true collision intersection volume. So the true collision intersection volume is the dotted line. The NeRF collision loss that we introduced is the solid line. This is upon the initialization, so you get lots of collisions, and then through various iterations of the solver, you eventually obtain a trajectory that has no true collision with the underlying mesh. And this is not only for drones, it's for really any robot where you can write down the dynamical constraints of the robot. So the first author, Mihao, likes to build robotic couches. I don't know exactly why. This is a fun hobby for him. So he wondered if he could use this method to navigate one of his robotic couches. And that's exactly what we did here, using a NeRF of the interior of a church. So of course, we need to to be able to quantify how good our planner is with respect to existing planners. And this is a little bit tricky because there are no existing out-of-the-box planners that work with NeRF environment representations. So we had to retool some standard planners to work with NeRFs. So our planners that we chose were RRT. You all probably are familiar with this. And then the minimum snap trajectory planner, which is a common tool for optimizing drone trajectories specifically, and it uses differential flatness. And so we had to take some sort of engineering liberties to make these work with the NeRF. But we did a kind of honest engineering job to make these things work with the NeRF. And we find that along these three metrics, so the collision metric, which I introduced, the control cost metric, which I didn't talk about, but it's just the standard quadratic control cost, and then the failure rate of the solver. So how often does it actually find a feasible trajectory from start to goal? These are all lower for our solver compared to these RRT and min-snap solvers. Okay, so trajectory planning is only half the story, right? Once you have a trajectory, you need a way of measuring your pose at each instance along the execution so that you can correct when you float away from the trajectory. And so to this end, we introduced a state estimation scheme. You could say something like a Kalman filter, but it works on principles very different from the Kalman filter. And basically this state estimation scheme blends the optimization of two costs. One is the photometric cost. So I know where I think I should be, and then I have the onboard camera image that I've taken, and I can render the image from the NeRF from where I think I should be, and those two images are going to be different. So then I can optimize the photometric difference between those images to figure out where my pose should be. But I want to balance that against my confidence in my dynamics, which tells me, where my pose should be. So that in a Kalman filtering like Fusion, I want to have a process model cost and a measurement model cost. And so we do this, but in the context of an optimization problem. So we model our state, the full 12-dimensional state of the drone, with the position, the orientation, the translational velocity, and the rotational velocity. This is standard stuff. We represent this 12-dimensional state as a Gaussian, and it's the mean and the covariance of this Gaussian that we're trying to estimate through this estimator, through this recursive estimator. So we formulate a loss, which combines the photometric loss, this is what I just described a second ago, which has the synthesized NeRF image from our estimated mean, and then the ground truth image, which the robot has captured with the onboard camera. So we want to minimize that photometric loss. And then it also has the process loss, which says, okay, given my prior mean, this is where I should be right now, and I want to minimize my mean estimate against that. So I optimize this objective function again, using the Atom Optimizer and PyTorch using AutoDiff. I have to use AutoDiff because within this objective function is the NeRF rendering. So again, I have to differentiate into the NeRF neural network. And the minimizing argument is now the mean for my posterior. And then I can also acquire the covariance for my posterior by finding the Hessian at this mean position, which again, I find through AutoDiff.
Do you want to allow a question in between? I think Florian has a question.
Sure.
Yeah, Florian, go ahead.
Hi, Mac. Excellent talk.
Thanks.
I was wondering, when you optimize the orientation of the camera based on the observation, isn't that easy to fall into local optima into, and how do you handle the trickery of that type of optimization?
It is, yeah, that's a great question. So basically there are two tricks here. One is that we use the dynamics prior to give us a pretty good warm start, so we know that the camera pose is in the correct neighborhood. And then when we're optimizing for the photometric loss, we sample points in the neighborhood of SIFT features. I think we use SIFT features. We use some standard feature. So we don't formulate the loss over all pixels in the two images. We just subsample, and that subsampling happens at every iteration of the optimizer. So they're different all the time. And then we have a higher likelihood of sampling in the neighborhood of a feature, as identified by a classical feature descriptor. Does that make sense?
Yeah.
Okay.
Thanks very much.
Yeah, and it is still subject to local minima. I mean, yeah, this estimator certainly can fail, especially if the true pose is very far from your initial guess. Thanks. So, right. So we have to compare against existing methods, and the only existing method at this time was iNeRF, which I talked about before, which is very similar to what we've done here, but only uses the photometric loss. It does not use the dynamics prior, and iNeRF only optimizes for the 6-dimensional pose. It doesn't optimize for the full 12-dimensional state, the dynamical state with the pose and velocities. So it turns out that, so basically what we do is we include the extra information of the dynamics of the drone, and that helps as it should. So our mean is in red and our covariance is in kind of brown, and their iNeRF mean is in green and their spread is in green. So you see that we do better and we have a narrower spread in rotational error and translational error. In rotational velocity, it turns out there's not a whole lot of difference, but in translational velocity, there is a big difference. And iNeRF doesn't give you the velocities, so we acquired the velocities through post-processing with a finite differentiation between successive iNeRF solves for the pose. Okay, so then we combine the trajectory optimizer with the state estimator, put them together in an MPC loop, and this is our feedback controller. So we plan, and then we execute one step, estimate the state after that one step, and then replan from the new state and do this again and again. And it turns out this is really important. If you have any dynamics error, so here we have an error in our model of the dynamics, with the MPC, we can be robust to that error and successfully fly through the play structure. If we were to just execute open loop, those errors would compound and eventually we'd crash. And this is also true for external disturbances, not only modeling errors. So here we have a large external wind gust, and through this MPC, we can still pass through the Stonehenge arch. Okay, so now we can navigate a robot through an MPC sort of planning and state estimation scheme using a NeRF as a 3D map. How about grasping and manipulating 3D objects where the object is represented as a NeRF? So this is primarily work by my former PhD student, Preston, who's now a postdoc at Caltech with Aaron Ames. The substance of the problem here is that the NeRF does not tell you a deterministic surface. And it shouldn't, because we don't know a deterministic surface, right? We only have a bunch of RGB images. So if we had a model that gave a deterministic surface, it would be overly confident. The NeRF, one of the beautiful things about the NeRF is it fairly represents the stochasticity about the surface, about the geometry. And so one way to think of the NeRF is a collection, a continuous collection of nested surface proposals, right? With every density level set, you have a different shell, which can serve as a surface proposal. And so how do you plan a grasp for an object where you don't know the surface, but you have actually a whole continuum of possible surfaces, each with a different probability of being the correct surface? And the idea was basically to co-opt the concept of ray tracing that the NeRF is built on to synthesize images. So we basically co-opt that concept and retool it for grasp optimization. And so we call this grasp ray tracing. So first, let me explain, or let me try to convince you that this kind of, the fact that we don't have a deterministic surface is really a problem and not an easy problem to solve. So let's consider a pre-trained NeRF of a cup like this, and let's take three kind of hypothetical fingertip locations and consider moving those fingertips from those initial locations towards the interior of the cup. And then let's kind of probe the density of the NeRF at each of these locations. It looks like these three different curves, each one with a different color. You can see that the spread of the density is different at each of these fingertip locations. And you can see that the sort of maximum, the kind of maximum density is reached at different ground truth distances from the true surface. And so it's really hard to know if you want to pick one surface to call the surface. It's really hard to know what surface to pick, because what is the surface here, if you were just to pick the maximum density value, for example, would not correspond to the density over here. So what to do? We really need to think probabilistically about the surface. So let's go back to ray tracing to produce an image. How does ray tracing work? Again, you sample the NeRF based on the density of the NeRF along a ray, and then you use the samples as weightings, the density values as weightings, to produce a weighted average of the color to give you an expected color at that pixel. And this is literally probabilistically an expectation computation with a Monte Carlo approximation. Our insight is that you can compute expected values of all kinds of things, not only pixel color, but all kinds of things. So for example, you could, and this is what we do, compute an expected value of a grasp metric. So you take these candidate fingertip locations and candidate ray directions, move your fingers along those ray directions, compute the grasp quality with an existing grasp quality metric along each of these sample locations, and then take a weighted average based on the NeRF density, and you get an expected grasp quality metric. And then you could imagine optimizing the fingertip locations and the ray directions to optimize this expected grasp quality. That's essentially what we do, but there's a little caveat here. So this would be what we call a risk neutral grasp metric. But really, in grasping, errors are catastrophic, right? If you get the grasp wrong, if your object falls out of your fingers, that's a catastrophic loss. And so we really want to take a much more risk-sensitive approach. And so what we do is we use a common trick from risk-sensitive planning or risk-sensitive control. It's called the entropic risk metric. It's basically a soft max. So we take the grasp metric evaluated at each of these sample points, multiply by a constant gamma, which is a user-defined constant, and then exponentiate. And the exponentiation basically stratifies the difference between all of these grasps and very much more heavily weights the bad grasps versus the good grasps. So we're being pessimistic here. We're saying the bad grasps count a lot more than the good grasps. And then we take the expected value of the grasps. And then we take the log to get the scale back to a good numerical scale for optimization. And this is our ultimate loss. And we now optimize using, in this case, we don't use stochastic gradient descent. We use the cross entropy method, which is a common optimization technique that's used in, for example, reinforcement learning that's very successful. We find that this allows us to escape lots of local minima, and there are lots of local minima in this problem. And so this is an example of a resulting grasp. So now we have only a NeRF of this underlying teddy bear. We have this tri-finger robot platform, and we plan our grasp trajectories. Now, it's not just a single grasp, it's a grasp trajectory. The fingers go in, try to execute that grasp trajectory with an underlying tracking controller, and then they end up contacting at unknown locations the surface and then of the object, and then they execute a lifting maneuver to lift up the bear. So this is the high-level idea. This is still work in progress. We don't have a publication on this yet. We hope that'll come out soon. So I can't point you to a reference, but hopefully I'll be able to update through a Twitter feed soon about a paper on this topic. Okay, so now I'm going to switch to the concept of building a physics simulator designed specifically for objects that are represented as NeRFs. So we can now navigate a robot using a NeRF as kind of a 3D map of the world. We can grasp and pick up objects that are represented as NeRFs. Now, let's kind of think of a grander vision. And so what is this grander vision? Well, this is mostly the work of my PhD student, Simon Lecleach, who just recently defended his thesis, actually. The grand vision is to automate the instantiation of a physics simulator. And I feel like this is actually a really kind of important untapped problem in robotics. In robotics, oftentimes you need a simulation of the scenario, right? And how do we get a simulation of the scenario? Well, we have either a highly skilled engineer or a highly skilled grad student sit down for 2 months and build out that simulation in PyBullet or in Mujoko or whatever, right? You import the artifacts, you have universal robot description files for all of the objects and for the robot, and still it doesn't work, and you have to just fight with the simulator, and it just takes a lot of engineering human expertise to do this. And I think this is unsustainable if we're thinking about real robot autonomy. In real robot autonomy, you want a robot to enter a completely unfamiliar scene, knowing nothing about the geometry or the objects that populate that scene, and then given sensor measurements, instantiate from nothing a physics simulation of the scene. And then you can use that simulation for all kinds of counterfactual reasoning. What if I do this? What if I do this? What if the robot picks up this thing and throws it over there? What if the robot executes this trajectory? And then you can use that for task planning and for trajectory optimization. That's the overall goal here. So here's the concept in a little bit more fine-grained detail. Atlas robot walks into a room, looks at the Stanford bunny, takes a bunch of images of the Stanford bunny, and builds a NeRF of the Stanford bunny. We can already do this. This is state of the art already, right? Now, what we propose to do is augment this NeRF of the Stanford bunny with a bunch of qualities that are important for simulating the Stanford bunny: surface normals, mass properties, center of mass, friction coefficients, and so on. And then we import this object as a simulatable object into differentiable simulation engine. We have our own in-house built engine that we've called Dojo, that was developed by Simon and a collaborator named Taylor Howell from Carnegie Mellon. So we import the NeRF into a differentiable simulator, and then we can simulate scenarios. Like the Atlas robot can say, well, I've never seen this bunny before, but I have this ball, and now I see the bunny. What happens if I roll a ball at the bunny? What's going to happen? Oh, it's going to move in this way. And then now that it has an auto-differentiable simulator, Atlas can plan or do all kinds of things. So firstly, he can look at the difference between his actual actions in the environment and his simulated prediction of those actions, and use that for parameter identification to fine-tune the simulation, to, for example, fine-tune coefficients of friction. He can use it for planning. So he can say, okay, if I throw the ball in just this way, I can get that bunny to move to this desired location. And he can use it for policy optimization. So he can optimize the weights of a neural network that allow him to pick up the bunny or navigate through the scene, for example. So that's the high-level concept. So just to kind of drive home the power of taking deep learning concepts to get the geometry and then pairing those with model-based physics simulation, Atlas can think of a myriad of different options. He can think of what happens if I throw the bunny at the ball rather than throwing the ball at the bunny. Now, if we're thinking of a purely data-driven approach, where we're trying to, through a deep network, do the simulation of the physics, that would be impossible unless Atlas had seen examples of the ball thrown at the bunny and the bunny thrown at the ball. In what I'm proposing, Atlas has not seen examples of either. He's only seen the bunny, but he has a physics engine and he knows the laws, the universal laws of physics that govern what will happen when a ball gets thrown at the bunny. Okay, so the core here is this processing the NeRF object to make it simulatable. And this is what we call a Dano, Dynamics Augmented Neural Object. And just to kind of show you how well this Dano works, we take a ground truth mesh of the Stanford bunny in white, and we have the NeRF Dano object in black, and we put them both in our Dojo simulator and simulate them dropping on the plane, and you can see they're overlaid. That's the patchy white and black. They execute the same trajectory. So we retrieve very good simulation fidelity given only RGB images of this object, which is a little surprising. And we do this by computing surface normals, mass, center of mass, inertia matrix, and coefficients of friction. Some of these things we just have to guess at, like the coefficient of friction, we cannot know that from still images. So we just take a blind guess. In a little bit more detail, what we do is we compute these objects with a Monte Carlo approach. So we take the NeRF density, we sample based on a likelihood, with a likelihood proportional to the NeRF density value. So we sample high density values more likely than low density values. We sample a point cloud. And then with that point cloud, we also compute the outward facing normals at each of these points by taking the gradient of our NeRF. We take a Monte Carlo approximation of the mass just by taking a weighted sum of the density over this point cloud, the center of mass, again, with the Monte Carlo approximation, and the inertia matrix, again, with the Monte Carlo approximation. None of these are perfect. We don't know the true mass. We only know the NeRF density. And so there's always this unknown mass conversion between the NeRF density and the mass density. But the idea is that the idea is that the NeRF captures the geometry and the rest you have to sort of make reasonable guesses about. And so let me show you an animation that shows all of these things. So here's our NeRF sample points for the Monte Carlo computations. And then these are the outward facing normals. And then you can see that we can compute the center of mass approximately based on these sample points. That'll come up in a minute. There it is. Okay, so now what's really important here, like why do we need to compute all these things, is that we have to be able to compute surface interaction forces, collision forces and friction forces, right? That's really the hard part about rigid body physics simulation. And our approach here is to use these sample points to compute approximate normal and tangential or friction forces. And the way we do this is that suppose that we have an a plane that we're contacting, right? Some of our sample points are going to penetrate the plane. So we take that population of sample points. You can see that that's down here. And we, for each one of those sample points, we compute basically a spring force and a damping force based on the distance of penetration of that sample point. We sum up over all of those forces and we compute a resultant force and then also a resultant point through which the force is applied. So we have a resultant force and a resultant torque. So those spring and damper forces give you the normal force. And then we use Coulomb friction, just the standard Coulomb friction, which is the normal force times the friction coefficient in the direction to resist motion. And that gives you the tangential component. And then the two of those summed together is what I'm rendering here in yellow. And that gives us the contact force for simulation. And so with this, we can simulate motions of the bunny contacting a plane. If you throw the bunny on a plane like this, including rolling and all of this stuff. We can simulate contact between the bunny and primitive surfaces like spheres and capsules. And we can also compute collisions between the bunny and another bunny represented as a NeRF, or 10 bunnies represented as NeRFs. We can put 100 bunnies in a big bucket and throw them all in there and simulate the physics of that interaction. We can also simulate the contact between a bunny and a URDF, which you'd use to represent your robot. Right. Okay, so now what? Now what can we use this for? Well, one thing we've used this for is just system identification to fine-tune the unknown parameters of our simulator. So our simulator, as I said, we have no way of knowing what the friction coefficient is between the bunny and the surface. So we take a wild guess, and then we conduct a real motion with the real robot in the real world. That's shown in black here. Observe how the bunny slides, and then we have the predicted motion of the bunny from our simulator. That gives us a trajectory loss between the actual observed trajectory and the predicted trajectory. And then we take that as a loss and auto-differentiate through our differentiable simulator to fine-tune our estimate of that friction coefficient, so that now we have a more physically realistic friction coefficient, so that our future simulations are much more realistic. So this is multiple iterations of that auto-differentiation and gradient descent process to identify the friction coefficient. So now after 20 iterations, we've identified the friction coefficient, and we can simulate our simulator now represents reality much more closely. We can also do trajectory optimization. So suppose we want this robot manipulator, this panda manipulator, to push the bunny so that it slides and reaches a resting point at this black circle, and then comes back, and we want the end effector to sit at this white circle. And suppose we start with just some garbage initial trajectory, and we have a trajectory cost, right? And the trajectory cost basically says, okay, bunny, I want you over here, and end effector, I want you over here at the end of the time. And so now we can take that trajectory cost, back propagate through our trajectory rollout until we can optimize the parameters, the control parameters of that trajectory, to find a trajectory that optimizes our trajectory cost. That's what we're doing here. So initial iteration is pretty poor. And then at every iteration, we back prop through to minimize that error by tuning the control parameters until finally we get a motion that's pretty convincing. So this is using this whole pipeline for trajectory optimization. Now, I haven't shown you anything where we use this for policy optimization, which would be similar to trajectory optimization, but we store basically a full feedback policy through a neural network and optimize the weights of the neural network. This is something we're working on now. So hopefully I'll be able to show you that in the future. We have a paper currently under review. There's an archive paper that's posted out there. I unfortunately don't have the archive link here on my slides, but I'm happy to give you that link if you email me after the talk. So this is really all my technical material. So I talked about navigating a robot through a 3D scene represented as a NeRF. I talked about grasp planning, trajectory planning for a robot manipulator when the object is represented as a NeRF. And then I talked about building a full-featured simulation pipeline with objects that are represented as NeRFs. And the whole motivation here is that we want to be able to have 3D representations that come only from onboard sensing. So our robot only has a camera, it moves around, it takes those camera images, it trains a NeRF, and then you can do all of these things given that NeRF representation. Now, there's a lot of things to fill in. There's still a lot of exciting work to be done. And I'm happy to field questions and give you my thoughts on that exciting work. But these are some of our initial steps in that direction. So TLDR, what's the take home? I think NeRFs are going to transform robotics. I don't mean NeRFs literally in the conception of the NeRF, but I just mean neural network representations of 3D scenes. I think will become the standard in robotics. And there's just a lot of exciting research that needs to happen to milk or realize all the power of that neural network representation. You might ask, where are the real robots? I would ask that if I were listening to this talk. I showed you everything in simulation. So we're working on it. I haven't shown you any results here, but we do have a drone that can fly using the navigation policy that I described to navigate through our lab. And we'll have a paper on that soon. And just all I can say is invite me back next year in person, hopefully, and I'll be able to show you videos of real robots using these techniques. So I have to say thanks to all my collaborators. Of course, the real brains behind all this work is my grad students and my collaborators. They're all listed here. And thank you to all of you for your kind attention. And I'm really happy to take any questions or just to have a conversation about this idea. Thanks, everybody.
Mike, thanks so much. There is a huge amount of excitement along NeRFs and their integration with robotics. And as expected, I have to say almost, it was a fantastic talk. And it's always great to have you speak. And we have already a line of people who are having questions.
Great.
I will start with Xiao first and then followed by Florian.
Yeah, great. Thanks for the great talk. It's really nice.
Thanks.
The work are very exciting. Actually, about the Dano work. I'm wondering your comments on like the NeRF density and the actual physical density that can be used for physical simulation.
Yes.
Like in principle, like NeRF can learn the density in any arbitrary way. Like it can learn all the density on the surface, and the object will be hollow. There is no density within the surface.
Right.
Does that happen, or like it tends to learn a uniform density inside the surface?
That's an awesome question. I'm really glad you asked that. Yeah. It does not learn a uniform density. This is in practice, right? It's only empirical. It does not learn a uniform density, and it does not learn a hollow density. But either one is consistent with the visual data for training, right? So either one could be an outcome of the NeRF. But empirically, what we find is that the density is low outside the object. There's a fairly discrete but blurry transition on the surface. And then on the interior, the density value is highly stochastic. But the average density value is still much larger than in the free space. And so that's one of the motivations for our sampling Monte Carlo approach, is that we're trying to filter out the stochasticity and not really rely on any particular density value, that the average over all of the density values will be close to the same as if it were uniform. That's the hope. You can also imagine instituting priors that favor uniform density, right? To really favor spatial, let's say penalize high spatial variation, right? We've tried that and with not a whole lot of success, but I don't think we've fully explored that. I think that would be pretty interesting. And you also might say, well, the object could actually be hollow. That's absolutely true. The true Stanford bunny is hollow, actually. I don't know if you all know that. The true Stanford bunny is actually a terracotta lawn ornament. It lives in Jeanette Bogue's lab now. It's going through many hands, but it's sitting here in the CS department at Stanford. So it is actually hollow. And there's no way you can deduce that from the images alone, right? So what we propose in the simulation concept is that you start with your best guess from the NeRF of what the density distribution is inside. And then the only thing that matters for simulation is the center of mass, the total mass, and the inertia matrix. Everything else doesn't, that's all. You don't need the fine-grained density. You just need those three objects. And those objects you can do system ID on using the simulation. So you can watch real motion of the object and identify those parameters, which you may have had a bad guess starting from the NeRF alone. Does that make sense? It's an imperfect solution, but it's a hard problem as well. So that's what we're trying to do.
I see. Yeah, indeed, we can estimate the center mass and inertial matrix using SysID, but still during the collision, we are still using the density field in order to do the collision detection.
Absolutely, yeah.
Yeah,
so,
I see.
So one thing I didn't mention is that we actually, in our Monte Carlo sampling, we actually threshold a lower limit and an upper limit for the density value. So we don't sample points that are too high in density or points that are too low in density. We focus on a certain band of density because because collisions happen on the surface, and we're trying to get close to the surface without deterministically requiring a single surface, if that makes sense.
I see. Yeah,
Okay.
thank you very much.
So next we have Florian again.
Hi, Florian.
Hello again. All right, so amazing talk, and I'm really a fan of NeRFs, and we're using them in the lab. I'm just wondering about the future of NeRFs in robotics. So you mentioned voxel-based representations versus NeRFs, and I'm wondering any type of activity that requires sort of continually updating your NeRF model. Would that require that we solve continual learning for neural networks in its generality? Yeah. Or can we have a mix of voxel-based and NeRF-based representations that allows us to do dynamic updates? What are your thoughts on these types of updates?
That's a great point, and I'm sure you have your own thoughts on this, so I'd love to hear them. I think the distinction that I made at the beginning of the talk is now artificial. I think that the most modern NeRF variants, I'm thinking instant NGP and the variant which is implemented in NeRF Studio, they are actually fusions of voxel grids, not really voxel grids, but sample-based lattices and neural networks, right? And so I think currently the state of the art says that the best way to represent these NeRF properties, these volumetric properties, is start with a fixed resolution sample grid. And that sample grid can live in either an abstract feature space or in the NeRF density and color space, right? And then you have some combination of an interpolation scheme, which is usually continuous, like trilinear interpolation, which is what's done in instant NGP, I think I might be wrong. Maybe that's in planoxels. Anyway, one of the really well-known papers does trilinear interpolation to turn that discrete object into a continuous object. And some other papers use also a deep network decoder step that, like, if that grid is actually in some latent feature space, then there's a decoder that takes the interpolated value and turns that into the density and color. And the advantage is that when it's discretized like that, I think this is what you're pointing towards. When you have data, you can update it spatially locally, right? And so you can do it really quickly. And that's the trick with instant NGP, is you can update spatially locally very quickly based on data, versus with the original NeRF architecture where it's all in MLP, every point of data has to propagate through all the neural network weights. That takes a long time. So I think that these hybrid representations are the way forward. And I think in practice, we're almost there already. Like, I think that these grid-based representations, instant NGP can train in real time. In a matter of seconds, you can go from raw images. there's still a pipeline question, right? So instant NGP takes a bag of images and trains a scene in real time, but that's not a pipeline like where you start from nothing and you get one image and then you want to train a partial NeRF and then you get the second image and you want to train a new NeRF and the third image. So I think the pipelining is still an open question, and probably you guys are working on this. We're definitely working on this. I think there's a lot of systems engineering tricks that have to happen.
Got it. Thank you. We'll chat more later.
Great.
Okay, next we have two more, Ismail and Connor, and I would say these are the two last questions, so we can go into the smaller meetings. Ismail, you're first.
Oh yeah, thank you. So you mentioned that you wanted to implement this algorithm for like NeRF and stuff on real robots.
Yeah.
What do you think are some of the bigger challenges to that?
Yeah. The number one challenge is compute. NeRFs still require big, beefy NVIDIA GPUs to compute. NGP, if you want it to run in real time, needs a big state-of-the-art graphics card. And I think probably the Xavier board with an NVIDIA graphics card, we have not tried computing NeRFs with an Xavier board and the associated graphics card. I don't know exactly what the graphics card is on that board, but that's probably getting there. I mean, I would assume that you can train a NeRF in a matter of minutes, maybe on that kind of compute hardware, and then you can integrate that with a modern robot, with a drone or with a humanoid or a manipulation robot, whatever. Honestly, I think probably though a much better model is to think of cloud robotics and think of compute as an abstract resource that lives in the cloud, and then rely on networking. So have your robot be basically a front end to a cloud-based computing system, right? Basically, your robot's a device and it's an edge device where you capture data from the robot, maybe do some light pre-processing on board, and then do the NeRF training or generally neural network training in the cloud. And I think that's also really exciting. There's a lot of open questions to tackle there, but that is our current model for making robots work with NeRFs in real time, in real life. That's what we're working towards in my lab right now. Okay,
and then one last question by Connor.
Actually, my question was, I was going to ask about compute as well, and just how far away we are from, well, even if you're doing cloud-based stuff, like, are these algorithms running in real time, or are they still far from real time?
Yeah, so that's a great question. Yeah, so NeRF training it depends on exactly what you mean by real time, because virtually all the NeRF training that I've seen, even for SLAM paper, there are a few NeRF SLAM papers, even for those papers, it seems that what is actually happening is that the data is batched and then processed in batch. So that's the only benchmarks I have for you are that model, which is not the right robotics model, right? The right robotics model has to do with time lag and like continual training. And I don't know about that. But if you think about batch, you can train from zero, given a batch of data. You can train a very good NeRF in a matter of seconds. Of course, it's garbage in, garbage out. So you need lots of good data to get a good NeRF, but you can train it in, so you can start to see the 3D geometry coming together in about 5 seconds, and you get a very good NeRF in 15 or 30 seconds. And this is not my work. This is work, so this is implemented in NeRF Studio, which is a wonderful platform for NeRF development and NeRF research that comes out of Berkeley. And I think the technical milestone that opened the floodgates was Instant NGP, which is a paper mostly from NVIDIA authors. So that's the NeRF training. The stuff that I talked about as my contributions here, the trajectory optimization, the grasp planning, the simulation. So the trajectory optimization is not yet real time. It takes on our on a laptop, it takes about 4 seconds to resolve. When really you want it to be at about 10 hertz. So we're probably a couple of orders of magnitude away from real time. But we have a completely different trajectory optimization scheme that I talked about the one here because it's already published and because it's pretty mature, but we have a totally different scheme that relies much more heavily on discrete graph search, and that we can already do in real time. It's at 50 hertz. So I'd say the published work is not quite real time for trajectory optimization with NeRFs, but I know my lab has already achieved this, but it's not published, and I'm sure other labs have as well. For the grass planning, that is not real time, but the concept here is kind of an offline online concept. So we plan the grasp offline. Maybe it takes a couple minutes, that's typically what it takes, 2 or 3 minutes. And then we execute online with a trajectory following, sort of path following controller for the fingertips. The trajectory optimization piece is completely online. In fact, it's, sorry, not I misspoke. The Dano simulation piece is completely online. In fact, we can do these simulations at 100 Hertz. So in that segment of the talk, we take a pre-trained NeRF and we compute this Dano object, and that takes it takes a little bit of something on the order of seconds, like maybe 30 seconds, something like that. So once you've computed the Dano, then you instantiate the simulation and run the simulation, and that's instant. That's at 100 Hertz. So that's pretty fast.
Okay, great. Thanks for this is a really insightful talk. It's cool to see all the directions that NeRFs are going in.
Great, thanks.
I actually just had one very small question.
Sure.
Do you foresee using like force feedback information for improving those NeRFs, or improving your like obviously improving the dynamic model, but maybe even improving the density estimations of the NeRF?
Yeah, definitely. I think that's wide open research territory. So force feedback to get mass properties, definitely, but also tactile feedback like gel site style sensors to get really detailed fine-grained geometry information. That would be really useful. And so one thing that's so cool about this NeRF concept is that it's really modular with the kinds of sensors you can. So the original NeRF was only RGB images, but you can, by now, there's already infrastructure, open source infrastructure out there that you can train with a fusion of both RGB and RGBD images. And where we ourselves are working on being able to train with also point clouds from LiDAR. So you can have RGB, RGBD, and LiDAR from 3 separate sensors, all informing together one NeRF model. And conceptually, that's totally easy. It's just a matter of software engineering to build the pieces to make that happen. And so it's not at all hard to, conceptually, it shouldn't be hard to incorporate touch sensors as well, or force sensors as well. Conceptually, there's a lot of software engineering that has to happen to make that a reality.
Thanks so much.
Yeah, okay, Mac, thanks again from my side. It has been really an amazing talk, and also a huge interest in this area. It's super cool to have had you here, and I look forward to have you here again once you also execute a lot of this on the robots. Thanks so much everyone for attending. Great that so many of you came, and as you see, it was more than worth it. And Mac, you just stay in the room, and then we can have a few smaller chats.
Great, thanks Igor. Thanks everybody.